Okay, this is a video on section 1.1 in calculus, going over some of the highlights. The first is going back to, probably you first learned this in Algebra 2, and a relation is any association between two variables. So for example, this could, and any set of ordered pairs. So this could be a relation. I could have 1 go to 2, I could have 1 go to 4, I could have 2 go to 5, or -3 go to 7. That's a relation. Any association here with between two variables. What makes something as a function is every input only goes to one output. So every input goes to one output. So the above set of ordered pairs that I just did would not be a function because the input of 1 can't go to 2 and cannot go to 4. And you can see why in the real world this would be important. I want to know when I input something, whether it's a code. I often use the vending machine example. If I'm interested in getting something from the vending machine, I want to know when I insert a particular code, I want to know what I'm getting out. So if I want a Diet Coke, I'd be pretty disappointed if I inserted a code and I could get a Diet Coke or I could get a Sprite. So a function is such that when you input a particular number or whatever it is or code, you know that only one thing is getting outputted. So that is the function. And graphically, how do I determine that an x value only goes to one y value? Well, that would be what's called the vertical line test. So if I had a function like this, for example, any vertical line crosses the function at most once. So that would be a function. So every x only goes to one y value versus if I had something like a sideways parabola, that fails the vertical line test. So say this was the x value of 5. It has a y value that could be more than one thing. That's a problem with the function. So that would not be a function. The domain, as you probably know from previous classes, is the set of inputs, whereas the range is the set of outputs. And what we're going to be interested in terms of a domain is what can't it be. So two things to look out for what can't be in the domain are you can't divide by 0 and you can't take a square root of a negative value. So if you have a variable in the denominator, then there's likely a restriction on your domain. Same with if you have a variable under a square root. So let's skip ahead. I'm hoping interval notation is okay. So let's skip ahead to do a couple of example 2. And we're going to write the domain in interval notation. So in a of x, I notice there are some variables in the denominator. So is it ever the case that the denominator would be 0? Because if it is, then that can't be in the denominator. In other words, x times x plus 2 cannot equal 0, which means x can't be 0 and x cannot be -2. So when you go and write that in interval notation, well, I want to show that everything but these two specific values are excluded. So, and remember with interval notation, we always start with the lowest, which is -infinity, and I'm good. Everything's included till I get to 0. Can't be 0, hence the parentheses, which means excluding. Then it picks up right after 0, and I'm just realizing not 0. -2, everybody, is less than 0, so let's switch that. Sorry about that. So -2, and then picks up right after -2. And we're good until we get to 0, and then 0 to infinity. So that would be the way you would say, okay, there's a break at -2, and there's a break at 0. Those are the two values that are excluded. B of x is the exact same process. It's just I wanted to put a practice with factoring. So it factors to x plus 4, x plus 3, and the denominator could never be x can never be -4 or -3, so you would do the same type of interval notation. So then when we get to c of x, I don't have a variable in the denominator, but I do have a variable under the square root. So you want to start by saying 7 minus 5x has to be greater than or equal to 0. We can do the square root of 0, so it's important to include 0. So solving this inequality, we get x less than or equal to 7/5. So putting that in interval notation is -infinity to 7/5 with a bracket. D of x is super similar. I've got this square root and a variable inside, but because the square root is in the denominator, it can't be, I wouldn't set greater than or equal to 0. I just would say greater than 0, because remember, I can't divide by 0. So x is less than 3. So putting that in interval notation, -infinity to 3 with a parentheses instead of a bracket. Okay, so that's just a little bit of domain review and a little bit about functions. So if we go to this next page, evaluating functions means just when I put in a particular input, what's the output? But I want to look at example 4, because this is likely new, and it's going to have a huge importance in calculus. Something called the difference quotient, and I'm not expecting you to know what the heck that is and what its significance is. So right now we're just looking at the mechanics of it. And it's saying in this case, the difference quotient is I'm going to evaluate the function at 1 plus h, and from that I'm going to subtract evaluating the function at 1, and then I'm going to divide that difference by h. So let's do that. And in order to do that, let's maybe to the side before we put it all together, let's just find out what f of 1 plus h is. So remember what we mean when we're evaluating a function. It means wherever there's an x in the function, I'm going to put, in this case, instead of just putting a number, I'm going to put 1 plus h. So my function was f of x equals x squared. So for every x in the function, I'm going to put 1 plus h, so it's going to be 1 plus h all squared. And then so that's going to be the f of 1 plus h part. And from that, I'm subtracting f of 1. So this is easier. F of 1, wherever there's an x, I'm just putting 1 this time. So it's going to be 1 squared, which is just 1. Okay, so let's put it all together in the difference quotient. So the difference quotient says I'm going to put f of 1 plus h, which we just said was 1 plus h squared. And from that, I'm going to subtract f of 1, which we just found to be 1. And you're going to divide that whole thing by h. All right, so now let's just simplify it. If I FOIL out 1 plus h squared, I get 1 plus 2h plus h squared minus 1 all over h. Okay, so let's simplify. What can we combine? Well, we certainly can combine the constants. So the 1's go away. They cancel each other out. 1 minus 1. And then on the top, I'm left with 2h plus h squared. And what can I factor out of that? Out of the top, I actually can factor out an h, which gets me 2 plus h. And that allows me to cancel the h in the denominator. And just kind of a little kind of hint about this is when we're finding the difference quotient, you kind of can be rest assured that you've likely done the right process if the h in the denominator ends up canceling. And you'll see why that's the case a little bit later. But if you simplify correctly, that h in the denominator should go away. So this is what the difference quotient simplifies to. So I feel like for most people that's new. So I wanted to highlight that. And then the last piece I wanted to highlight, no pun intended, is the piecewise function. So a piecewise function means it's a function where depending on where you are in the domain, you have a different formula for the function. So this piecewise function here in example 7 happens to have 3 separate pieces. So when you're doing what's asked, which is computing the output for given inputs, I want to look to see which of the pieces I'm going to use. So if I'm finding f of 1, I'm looking at these restrictions and figuring out, okay, for which one do I use if I have an x value of 1? Well, 1 is less than 2, so I'm going to use the first piece of the function there. So in other words, I'm going to plug 1 into 3 over 4 minus x. So 3 over 4 minus 1 is 3/3, which is just 1. So if I'm finding now f of 2, well, 2 is not included in the first piece, but it is included in the second. So I'm going to use that formula for the piecewise function. So I'm going to input 2, and I get 4. And finally, f of 3. Well, 3 is not included in the second piece, but it is included in the third. So I'm going to use the third for 3. So it's 3 squared minus 5. Or the square root of 9 minus 5, square root of 4 is 2. So piecewise function, you got to be careful of where you are, what is your input, and based on the input, you're going to look at the restriction to see which piece you're going to use to evaluate that function. Okay, and a little bit before I look at a couple of the homework things, just a little bit about 9 in your calculator. Whenever I give you a window, like I've given you here, you're going to go to window in your calculator, and it's always going to be the X window by the Y window. So -4 in this case is you're going to put that in for your X min. 4 is your X max. -0.5, the second piece here, is your Y min, and 1.5 is your Y max. So one of my goals this year for you all is to get comfortable using your calculator, all aspects. So this is obviously the graphing function in your calculator. So make sure you meet with me if you're struggling with that. Okay, so looking at the homework problems, let's look particularly at the first problem. And then number 4, which is is graphing piecewise functions, I want to look at that too. So the first problem says it's another difference quotient, right? So remember with the difference quotient, you have a couple pieces in the front, so in the top rather. So it may be helpful to do them separately, because what the difference quotient says is you're going to evaluate the function at 3 plus h, and from that, you're going to subtract evaluating the function at 3, and then divide what you get there by h. Now, this time the function has 2 separate terms. It's 3x plus 2. And when you evaluate a function, it just means wherever there's an x, plug whatever your input is in for x. So I'm going to say 3 times 3 plus h plus 2. Okay, so that's my f of 3 plus h. And let's just simplify this a little bit. So I've got 9 plus 3h plus 2, or in other words, 11 plus 3h. That's the f of 3 plus h. F of 3 is a little easier. You're more used to that. When x is 3, the output, it looks like, is 11. So now let's put it all together into this difference quotient. So the difference quotient says, take f of 3 plus h, which we just found to be 11 plus 3h, and from that, subtract f of 3, which we said was 11, and divide that by h. Okay, so the 11 cancels, so I'm left with 3h over h. And remember what I said, if you're doing it correctly, the h in the denominator should go away, which it does, and so we just get the difference quotient equaling 3, which is very nice. Okay, final problem I want to do together is another piecewise function, since it seemed like people were shaky on this. The first part A in number 4 is just like the other. So if I'm looking to find f of 1, well, it looks like 1 is included in this interval of this first piece. So f of 1, I'd use the first piece, or root x. And so f of 1 would be 1. When I do f of 2, well, that's included here in this second piece. So I'd plug it into the second piece, which happens to be a line. So 1 plus 2 equals 3. And finally, f of 5, well, 5 also is included in the second piece. So f of 5 is also on the line 1 plus x, so 1 plus 5 equals 6. Now, one thing that's always hard about piecewise function is actually sketching what the graph looks like. So one thing that might be helpful is looking at the actual equations. So root x, I would say, maybe I'll do a highlighter. Root x, it's important to know that that's slow growth. So a square root function, in general, a square root function, like if I were just doing the square root of x, it looks like that. Again, the slow growth. 1 plus x is a line, and x squared minus 19 is a parabola. So that's just helpful to know the general shape when something is curved versus linear. Now, in terms of graphing a piecewise function, you always want to make sure you're graphing the extremes of the restriction. So for example, I need to, in the first piece, plug in both 0 and 2. So when I plug in 0, the square root of 0 is 0, and I'm going to put a filled-in circle there because 0 is included in that piece. So now I'm also going to plug in 2, and when I plug in 2, I get the square root of 2, which is about 1.4. So, but it's going to be, I'm going to put an open circle there because it doesn't include 2. It includes all the way up to 2, but exclusive of 2. Okay, so now let's go to the next piece, 1 plus x. I'm going to plug in 2 again, and when I plug in 2, I get 3. So there's going to be a filled-in circle at 2, 3. And let's plug in the other extreme, 5. When I plug in 5, I get 6. So 1, 2, 3, 4, 5. So 5, 6. And again, I'm going to fill it in this case because it's inclusive. I can see in the restriction that equality is included. And 1 plus x is a line. So I'm just going to go like that. Okay. And the last piece we said was a parabola, so you shouldn't make it linear. It should be somewhat curved. First, I put in 5. When I put in 5, I get 25 minus 19, which happens to be also 6. If it didn't land right on 6, which is already filled in, I'd have an open circle wherever that output was because it doesn't include the 5. But because it's already filled in, I'm just going to keep it there. And then you can plug in one more point. If I plug in 7, I get 49 minus 19, which is 30. So we're getting pretty big. So we know that this piece is curved. It's like a parabola here. So I'm just going to draw it like that. And so that's a sketch of our piecewise function. Important to remember, you always plot the restrictions. If it's a closed, if it includes equality, closed circle. If it doesn't, open circle. But just remember that open circle might end up getting filled in by the next line. Okay, that's 1.1.